Log on, tune in, find out. Another good idea from Cambridge.
We'll discuss the usefulness of predicates.
Okay, thank you. So this is some work in progress, by the way, or more or less in progress, and it's joined with, well, you can't really say, but it's with Parastream. And so I made a definition because I could prove a great theorem, and then I convinced myself that's actually a good definition also. So I'll start with the definition, and then you'll see where it takes us. But any comments on, what one should call things, and if these are bad definitions, and, please. So I start with my favorite subject, and that's sort of max CSPs. And I wrote two of so one max CSP is max 3 sats. I give you a set of 3 clauses, and you want to find an assignment that satisfies the maximal number. So another thing is that we can also have linear equations. Instead of having sort of the OR of 3 variables, we'll take the XOR, and then we have sort of really the same instance, but we have OR instead, and we want to satisfy as many as possible here. Okay. And just so to fix some notation. Now I can't. Indices, how do you spell this? Like this? There should be an I, no? Which of them is an I? This is an I. Thank you. Yeah, so a condition like this, I'll write like this. P is a k arity predicate. I have k negations, which you see on the board over there. I have k indices, which are the indices. This is sort of short term. And what I want to do So, and I'm interested in, most of the time I'll be interested in efficient computation. So I'm given an instance, a set of negations, a set of indices, and I have m constraints, and I really want to maximize the sum of these things. Okay. Okay. So how well can you approximate this for in my 2 favorite cases? So let's see. I forgot to write So traditionally we've been interested in approximation ratio. Well, let's see. And the approximation ratio I'll be interested in is you look at the number of satisfied conditions by the algorithm divided by the optimal value. So this is at most 1. If it was 1, we would really find the optimal one. So let's see for our 2 favorite. How well can we approximate max 3 set? Somebody who doesn't do this for a living can try to figure this out. Well, Nishit is. Well, either everybody does this as a living, or it's just
approximately 87% more than.
Yeah, that's so we have a trivial algorithm. So the really trivial algorithm is say, well, this is a difficult problem, just give random values to the variables and see how well we do. And for 3-sat, if you look at each condition, you sort of have 3 shots at making it 1, so with probability 7/8 you'll satisfy each clause. So this means you'll satisfy on the average 7/8 over m, and the optimum is at most m because you can't satisfy them more. So this is 7/8. And linear equations, a random one will actually give you satisfy each equation with probability 1/2. So my starting point is a theorem for all f greater than 0. So this is my own theorem from, I don't remember when actually, sometime. Maybe it was even before the turn of the century. So what happens is that you can't do better. So there's this trivial algorithm that gives you a 1/2 and 7/8, and it's NP hard to do better. Okay. And this I'd sort of like to call approximation resistance. So they're very hard to approximate. You can't do anything better than just mindlessly picking a random assignment and see what you get, and no efficient computation can do better. Okay. And now I've sort of spent a lot of effort trying to look at this property. Which predicates, what's the property of 3 lin and 3 max here that sort of, or 3 sat and 3 lin that sort of gives this property. Okay. So one thing in particular is that it sort of seems like a monotone property. In monotone in the sense that it's easier to get this the more things you accept. If you start with a predicate and add some more accepting states, and it seems like you sort of keep this a lot of the time, and I was trying to understand this. Okay, it isn't what?
That's not strictly true.
Well, it seems like, but it isn't. Okay, and there are some counterexamples to this being a monotone property.
Because of the ratio, because you're looking at the ratio.
Why it should be monotone?
Why is it not monotone? Because
There are some predicates. There is a particular predicate by Guruswamy, Levins, Sudan, and Trevisan that turns out to be approximation resistant. But there is something that accepts strictly a strict subset. It's not only on the number of accepted things, but the structure of things. Yeah, so it's even a subset, right? So you can extend it to a predicate that accepts one more, and it turns out not to be approximation resistant.
If you change the alphabet, make a larger alphabet, this is the same? Because you can translate it back to...
Yeah, I'm built only over the binary, and people didn't work that much over bigger alphabet, but you can translate everything, right?
Translate everything, so essentially solving this problem solves all the other problems.
Oh, you mean in that sense?
No. I mean,
More difficult problem.
Well, let's keep the alphabet small. Let's not get... Okay, so I couldn't solve this problem. So now I want to extend it. You want to come up with a different definition where you can actually solve things. Okay? Okay. So we have our P. And so the more general notion I'm after is sort of saying, well, it's sort of very natural. You're giving something here, and you sort of, where do you get approximation resistance? Well, I sort of promise you that there is one solution that you can satisfy this almost all the time, or even all the time, and your task is to find something that does about equally good. And on, if 3 sat, there isn't much you can do, but suppose this was majority on 17 variables, then in fact it makes sense to give the algorithm credit if it almost gets majority right. So I sort of want to say that the measure of the performance needn't be really the same condition. Okay. So I want to define P useful for Q, okay? And the idea is that so how do we define this? So here's something I don't really like, We would really want to say that the maximum is everything, but I'll say that it's almost everything. So there is some assignment that satisfies P on almost these things. Okay. So there exists a delta such that for sufficiently small epsilon, and you need an M here. Well, this is just the E of Q is just the sum over all x. Right, it's the expectation of Q where you pick things randomly, and that's what you would get by the trivial algorithm. Okay.
The reason why a Q was going to the rails?
Yes, that's the most general definition. Or, well, it's sort of just saying that, we could have it into 0, 1, right? Well, but I'll return to this. I mean, at least that forces me to treat the 0, 1 case. That's a special case of the reals. Okay. Okay. So let's write some definitions. So I'm not sure if I have to. So if I define useful, useless is, you understand, right? Okay, that's the negation. Okay. So as Madhu pointed out, I can always use any, predicates that takes just values 1, 0, 1, I can use this for Q. So if I say that P is useless for P, could you rephrase this?
It's useless for P.
It's approximation resistant.
Good. This is what I just a minute ago. So this is P approximation resistant, right? Are you happy with the definition? Maybe I'll.
So you say that there exists a polynomial time algorithm that finds.
Yeah. Good. So.
Does want to find mean can find?
What?
Want is not really want, it's more like there
Well,
exists.
Yeah, so that's sort of a little bit colloquial, right? Exists probabilistic polytime algorithm. That finds. But let's do something simple first, and then before we sort of goes into efficient computation, we can just to get some feeling for this, we can think about information theoretic usefulness. I mean, does this even, if P is equal to Q, of course, there's an easy guarantee, but for other pairs, as you realize, I'm soon going to generalize this to well, P are not equal to Q, and then you could sort of ask, does it even exist?
You put 2 Q's there,
I did. I wanted 2 Q's.
so I don't understand.
No, but that's always happens.
You still have the promise with the P's.
Yeah, you have the promise of
Oh,
the
the
P's,
promise
right?
is with the P's.
Yeah.
Okay.
So this, sum of the P are,
This should be delta.
well, yeah, plus delta even, but even, yeah,
Greater than rather than
you know what I mean. So yeah, so E of Q plus delta M, and we have this is, and here if we're talking information theoretic, it doesn't really matter, the epsilon won't play into a role. So let's see, suppose, suppose P is parity here of k variables, say, and Q is the negation of parity. Okay. So is this information theoretic useful? Is P information theoretic useful for its own negation Q?
Useful in this sense?
What?
You ask useful in this sense?
Yeah.
Sense?
Well, in the information theoretic sense, we're not asking for a probabilistic polynomial time algorithm. We're asking, is there, does this promise that the sum is, almost as big as it can be, or even as big as it can be, does it mean that there exists something non-trivial we can do for Q?
K is K even or odd?
That's a good question.
If
Pick
it's
your
odd, I
choice.
can do it.
If it's odd, you can do it, right? So it's useful if K is odd, because you just take the assignment that does well on P and just change all the variables, right? And then sort of satisfy the negation. But Avi, since you opened your mouth, what happens if K is even?
useless.
Yeah, it turns out you think about it for a while and it turns out to be useless. You can build examples where them, but you have to think a little bit to understand.
So let me just understand the definition of information theoretically useless for this pair. So
Yeah.
you'll say that there is an assignment, there is an instance on which you can satisfy all the parities P,
Yeah.
But on the negation of parities, you can satisfy at most a half.
Yeah, and in fact, I'll tell you the example. So you can even take parity of size 2 and take all pairs, okay? And you say, you know, that the parity of all pairs is even. You can take, you know, that's satisfied if you make everything equal to 1. But if you take the negation of parity, you can just barely satisfy half.
So it's like marks cut on a complete graph.
Yeah, yeah. But you were supposed to figure out this online. Okay? So let's have a first definition. So it's also called computationally. So now I want to sort of the nice definition I said, you know, something is computationally useless if it's useless for every Q. Okay? So no matter which real valued function you take, you know, you can't do anything. Okay? So now you can start proving theorems.
I have a question.
Yes?
I'm confused. So, if Q is not approximation resistant, then anything is useful for it.
No, because it'd be better than the expectation.
But the
No, yeah.
Trivial,
Because the promise is not that something satisfies Q a lot of the time, right? The promise is that something satisfies P a lot of the time. So it's really a property of P.
it's actually it's confusing. So,
Yeah.
say something illuminating about this.
Well, yeah, so that this really this
Should be obvious.
P,
to me
P no,
that,
P is useful for Q.
yeah.
I mean, it's really more a condition on P than Q. You should think of Q as sort of related to P. It's a weakening of P. You know, the most interesting example is when it's, you know, P or almost P. It's sort of when P is 1, it's big, and when P is, when you're far from satisfying P, then you should have a somewhat big value.
No, but I'm also not following the definition now. So you said that if I give you that P is satisfiable,
Yeah.
then you should be able to do better on Q than
Average.
random assignment.
Yes.
But she's saying even without the information from P, she can do better than the random assignment because it's not an approximation resistant.
No, but I mean, you can do better than random assignment if Q is not approximation resistant. If you give an instance where you can satisfy Q all the time, right?
Right.
But you're not given such an instance. You're given an instance where P is satisfied almost all the time.
Right, but then I don't know what I can. I mean,
it's useless.
it doesn't mean that I can't. Yeah. So,
No, what? Can you give example of useless P?
I have a theorem.
okay. Yeah, okay. Fine.
Okay.
So what about the, I mean, for k equals 3 is odd, and you take
So this is computationally useless, right?
but you can negate, you can efficiently negate.
Yeah, but I give you an instance,
Oh,
and
you
the
get
promise
the-
is that you
yeah,
can
yeah,
satisfy
so-
parity. I mean, parity is, right? Parity is approximation resistant, so P equal to Q we know won't work.
Yes.
But I'm saying that no Q will work here.
Okay, good.
So the fact that I know that a given parity instance is almost satisfiable doesn't tell me anything about any other Q. That's
Yeah, yeah. You can't. I mean, it's not like it's not only that you can't satisfy the parity condition. Take any other real valued function, you can't beat the average. You can't extract any information about this set of triplets from the parity condition.
So-
But do you have an example where P is used for P, but other Q P is useful for that? Is used
Yes.
for that?
Yeah. So we'll
So-
get to this sooner
So
or
to
later.
ask about usefulness only of one function, you can have maybe a bunch of functions that together will be useful.
I'm just generalized to this, the condition to this. So what you mean by a bunch of functions?
A set of functions.
You want P, you want P or Q to be a set of functions?
P1,
P,
P2,
P.
P3.
The things should be useful. Maybe maybe parity alone
P.
is useless, but maybe a large number of parities.
Parity up to length K.
Well, I'm thinking of, predicate of 3 variables is a different predicate than the parity of 4 variables.
No, yeah. So maybe you have several predicates of 3 variables that if you know about all of them, then
But then you can look at the conjunction, right?
you can look at the conjunction. No, okay.
If you have the same set of literals, you can look at the conjunction, and if you don't force me to look at the same, I can sort of split it up into the various things. I don't think it matters much.
So
okay?
even the truth value, the vector of truth value for all of them will not give you any more usefulness than.
Yeah. Let's skip this generalizations. We have trouble enough digesting the one we have at hand, okay?
Oh yeah.
So let's. So I won't really prove this theorem, but so I'll. So the ways you do is you just take my parity proof, and what I used in my parity proof is sort of a PCP, and then you wanted to analyze this PCP, and then you had in the soundness you expand the predicate P you want to do by the Fourier transform, and then you prove that each term is small, and you do exactly the same here, and you don't have to change really a word of the proof.
So it's really parity does not imply anything about itself or smaller parities.
Or anything else.
Well, what's the Fourier transform, the terms are.
Yeah, that's fine, yeah. That's a good way to say it, okay.
Just to make sure it's for K even, this is obvious, right, from what we said before.
No, for K, no, it's not obvious. It's not.
It's
It's theoretically
computational
useless.
now.
For itself, for its negation, right? That's just for one function. We want it to be useless, we want it to be computationally useless. It should be useless for all Qs, right? In particular, this theorem contains the statement that that parity is approximation resistant, because that's implied by this, right? And it implies that any predicate implied by parity is also approximation resistant. So it applies lots of statements, right?
But this idea also means that if you are able to prove something for Qs which are parities, then you are done. If you want to prove that.
Yeah, that's sort of. Okay.
What did you just say about a predicate implied by parity?
Yeah, I'll say this a little bit more carefully, okay? So another, trivial theorem, if P is useless, and P of X implies, so we have a bigger predicate that accepts more things, then P prime is useless.
So useless is now in the computational.
Yeah. Now we've left the information theoretic. Now we're just going to do.
Never defined it, I think. So useless means useless for any Q. Okay, good.
Okay. So in particular, for the parity, it implies that anything implied by parity is useless, and in particular, it's approximation resistant, as we knew before. So to me, this sort of explains the fact that approximation resistance seemed to be monotone, because most approximation resistance proofs They didn't prove approximation resistance, they proved uselessness, and uselessness is in fact a monotone property. And before this is obvious in the sense that, the promise that P is satisfied compared to that P prime is satisfied is just a weaker condition that P prime is satisfied because it accepts more things, so it's sort of an obvious monotone statement. Okay. Yes?
The implication can be computational implication, or P implies.
This is only computational uselessness.
But even the implication.
The implication is a finite thing. Finite statement.
This thing, well, this says, since parity is useless, satisfiability is useless, right? Because
The question is, what did you mean by that? It's just saying that for every x, px is like
Well, we paid it.
right? This? Yeah. Okay. Okay. So now the idea is to try to characterize uselessness. Okay.
Is it useful?
Okay. So let's have a theorem, which is our Australian model. I think this is the way. So let me write, and then I'll explain if needed. So let's write first. Let's assume the unique games conjecture. So if you don't know the unique games conjecture, this is just the computational hardness of a specific problems that we sort of like. Okay. So the claim is that if you look at the strings accepted by P, if that supports a pairwise independent distribution, then in fact P is approximation resistant. Should I explain what supports a pairwise independent? Yeah, not enough nods for this, right? Yeah.
Parity would be an example.
Yeah, parity would be an example of size at least 3, right? Because that supports a pairwise independent measure. So this sort of, we want that the expectation of xi, according to the measure 0, and the expectation of xi, xj is equal to 0. No, it's not equal to j. Remember that I define things to be -1, 1. That's so if you have a measure where well, each point has expectation 0 and the product of any two has expectation 0, that's a pairwise independent measure. And for instance, if P is parity of 3 variables, you can just take the uniform distribution on all the strings accepted by it, and it has these two properties.
X is in, what does it mean xi is in?
Well, sorry, I was debating this here. This was just to remind you that the zeros come from the fact that we're in ±1, right? Okay, so this is a nice theorem. And
you're going to prove that's actually useless.
Good. So in fact, you don't even have to, you can just look at their proof and say, in fact, what they prove is uselessness. Okay?
Johan, the reduction is like exactly the same?
Yeah.
The analysis is different?
Yeah. Well, what do? They, on the soundness proof, they just, take P and use the Fourier transform and, prove that if any term is big, then and here, you have a real valued Q, but you have the Fourier expansion into any non-zero term and we're there, right?
Is this a useful theorem or a useless theorem?
Pardon? Well, they didn't know about my definitions. It's my theorem. But their proof. I have to change a word in it, in the end. And make things real valued.
The author.
What?
The author.
Yeah, and get rid of some of the authors. But so the thing I want to prove is that once you've got rid of this, and in fact put useless there, it's an if and only if.
It's an if and only.
And that doesn't follow from their proof.
No, this we have to actually to do something eventually instead of just defining things. Okay. So let's try to prove this. But
So otherwise you can use Gorman-Williamson or something. I mean, if it's
yeah, I'm going to do the proof now, but you have the right idea. Right, so what do we have to do? Well, we first have to make sure that, we have one direction, and to prove the reverse direction, we have to prove that P that doesn't, satisfy what we have in the theorem, will find some Q for which it's useful. That's the name of the game, right? It's not going to be useful for everybody. We'll have to find some Q where it's useful.
When you, in original formulation, when you say it supports pairwise independent measure, it's not necessarily uniform on.
No, it's it doesn't have to be uniform. It just supports. Whenever.
That's a statement that's harder to negate. I mean, conceptually.
Yeah, so I'll show you the if and only if here that you can conceptualize. Okay, so I'll say, that there.
You're missing a right graph.
So I claim that if it doesn't support a pairwise independent measure, there's some quadratic function, and it doesn't have a constant term. It has linear and bilinear terms. It doesn't have any quadratic terms, such that for any string accepted by P, this quadratic term is in fact positive. Okay. And this is just sort of a what is duality, right? So if this is true, clearly it can't be because anything where mu has positive support, this is true, and then this would be positive. But the expectation, I have rigged things such that the expectation of mu of Q is equal to 0, since the only terms where it appears have expectation 0, right? So, and duality sort of gives if and only if. Yes?
Repeat. What are you stating or proving?
I'm stating, and then I'm sort of hand waving myself slightly through the argument. Avi knows the proof,
He's telling you which Q he's going to pick to prove that.
Well, yeah. So I didn't say it that this is the Q I'll pick, but this is the Q I'll pick.
Which is, yeah, so yeah.
So P will be useful for Q.
This is a contrapositive of what he was trying.
Right?
Yeah,
So I have a P who doesn't support the pairwise independent.
Now you have some Q.
And I want to find the Q.
For which it's useful.
Yeah, and the Q I'm going to use is in fact the one that's guaranteed by this theorem.
Oh, so this is a lemma, like in your.
This is a lemma, yes, or a well-known fact maybe. I didn't find the reference for it, but it's not so hard to prove. One direction is easy and the other is duality. Okay.
So incidentally, this Q can be sort of negative valued.
Well, the expectation of it is 0, right? Because it's a quadratic. So we just have to beat 0 on it, because the expectation is indeed 0, because, even under the uniform distribution, every You know, both on the mu and on the uniform distribution, the expectation of Q is 0.
This is why you need real value Qs.
Good. Yes. So yeah, so this, so I'll get back to this, but this is correct. You know, so the theorem now is that P is useful for Q. Okay. Yes.
So Q has the same arity as P, right?
Yes. Yeah, right. It's a you know, it's just a real valued quadratic with the same inputs.
So in the definition of useless, you said, you know, it's useless for all predicates Q.
Yeah, of this.
Disputes it.
All of the same arities.
Well, I guess they have to be of the same arity.
Because otherwise it doesn't make sense, right?
Match. Okay.
And as Avi already figured out, this is sort of semi-definite program. So I don't have so much more to say, so I can, you know, do the details here. Right.
We tried to stop you as best as we could.
Pardon?
We tried to slow you down as best as we could.
No, that's good. I have some more things to say. This is sort of, I mean, the ones I've seen, Germans, Williamson, you just... So what's the highlight? Well, this is a nice quadratic function, right? Each of these conditions is a quadratic. When you sum, then you get a huge quadratic thing. And we know by this promise that, you know, there is a P which satisfies almost all these things, which means that when you sum the corresponding Q, you'll get a huge optimum. So you just know that the optimum is large, and then we sort of relax this by changing any pairwise product to the corresponding inner product of unit length vectors, and then you just solve this semi-definite program, and then you round it in a standard way. If you didn't...
when you say this is large, this is not like, it's not sort of 1 or whatever, if there is an absolute maximum that Q can ever attain.
No, but
it's like epsilon m.
Delta m.
Right? So
noticeable positive.
Yeah, so if it's at least, you know, the minimal positive value of Q times m.
Right.
Right, so it's at least on the form delta m for a positive constant m. And that's what I mean by large, and that means that the optimum will be large to the semi-definite programming, and then you just won't lose too much by the semi-definite rounding.
By the simplest roundings?
Yeah, so you have to be a little bit careful. So because you'll round in a two-stage process, you'll pick a random R, and then you'll sort of have probabilities that will be these inner products with these things. And you know, it will really, and first you'll solve this, you'll pick a random vector R, you'll take the inner product there, and interpret this as a probability, and that's the probability that you'll set xi to +1, and that sort of just works out.
UGC comes.
Pardon?
So the UGC.
Well, that comes in the.
Well, UGC you just need for the hardness, right? I mean, this algorithm is absolute. You get, yes?
Yeah, so in the algorithm, you need to make sure that the rounded xij is exactly proportional to the vi.vj.
Yes.
So that you could do. You could also do this Grothendieck, this Krivine argument kind of thing.
Yeah, I think there are lots of ways to do it. I did it my way as I knew how to do it, but there are more modern ways to do it. Okay, so yeah, so let me. So then you sort of immediately get the question. So as Nishit was pointing out, this is the reason I wanted to use this Q, and that's the reason why I needed real valued Qs. Okay. So the thing you might want, I don't know if it's more natural, but to have Boolean Qs, right?
Meaning useless only for Boolean Qs?
Yes, for predicates. If that is a more natural definition, which we can sort of discuss later, okay? So then you can ask, how about Boolean Qs? So let's. So the first thing that really comes to mind, since semi-definite program is our prime weapon here, is to take, not this real valued polynomial, but to take its sign. That's a completely reasonable thing.
So how do you interpret the sentence, how about Boolean Q? What is the... What is the question we're dealing with now?
Suppose P is only useful.
Well, P useless, I defined, P useless.
Okay, so now you're going to redefine uselessness?
Booleanly useless.
And then what is the question that you want to... Now you want to characterize this new modified definition?
Yeah, so then you said, suppose I had this definition, would we get the same class, or, would we get a nice class, or...
Okay.
So we take the sign.
And the obvious one that comes to mind is this thing, right? That's...
Then the expectation is different.
Well, and then you sort of stare at this. This is really where we want it.
Are you trying to say now that if P is useless, then it's...
So he's taking a P that does not support pairwise independent mu, and then trying to prove that there is a Boolean Q prime for which it is useless, for which it is useful. Yeah. And the candidate is Q prime there.
Okay. So now we have a theorem, and so we're supposed to really wanted this Boolean one. So it turns out that we can define a quadratic form which has the property that it's approximation resistant. Sorry, assuming unique games with it. Okay. And which means that, this P is not useful for itself, but it is useful for Q. So this is the example that I was mentioning before, that's something, where we know of a real valued thing for which it's useful, but not a predicate thing. Okay. So this is just an example, and I'm not sure how illuminating it is, but I'll tell you one surprising thing about this example that I didn't think would be true. Okay.
So Johan, this basically means that if you change the definition, you get a different class.
Well, I don't know that. I mean, they could be, it's not, this predicate P is not useful for itself, which is the most obvious candidate, but there could be other predicates it's useful for.
Particular sign by
yeah.
Another Q prime, yeah.
Yeah.
So this example shows that you cannot get the characterization for the Boolean usefulness, or
I don't know. So I mean
In
that.
any case, it shows that the obvious characterization or the obvious suggestion will not.
Well, no, the theorem might still be true with this other definition of uselessness, but it's not say I don't.
For this choice.
Not of this choice of yeah.
The sign of the degree 2 part of the Fourier expansion of P?
Well, can you repeat the question, please?
The sign of the degree 2 expansion, Fourier expansion of P.
Yeah, so I have to think about that. So I'll write some things while you're. So let's see what this example. Ryan, we'll see what this example looks like, and I sort of okay. So what does Q look like? Well, it looks like, you know. Okay. So this is just happens to be, I hope I got it right. Okay. So what properties do we need to do what we want? I didn't tell you what L1 and L2 are two linear forms. I might tell you what they are.
X is all variables x1 to x2.
Yes, x1 or, you know, these are each, you know, the sum of 5 variables, it turns out.
They involve x1, x2.
No, that don't involve x1, x2. Okay. So it's sort of, it has a measure which is almost pairwise independent in the sense that, well, we have the expectation of each single term is 1, and the expectation on the mu of each pair is 1, 0, except for this pair x1, x2 that I noted on the board. Okay. And the key property is that if you look at and the key property you want is that if you look at any Fourier coefficient, you know, of P, well, P is really, yeah, well, P is the sign of this thing, then any term that contains both x1 and x2 is 0. And once you have these two properties, you can sort of apply the machinery of Austrian-Mossel and get approximation in the system. I don't know if this sort of breaks your idea. This sort of related to, we can think about it. And this is sort of, so this is sort of just absurd, but before we see how this, let me just, when I started constructing this example, I didn't think this would work, and I'll tell you why I think it wouldn't work. Okay. 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 So, I mean, once you sort of have a predicate like this, it's not the sign of a unique quadratic. There are always lots and lots of quadratics for which, which give the same predicate. And in fact, the properties you have there, that there is a measure which, is pairwise independent except x1, x2, is exactly saying that, the term x1, x2 must appear in any representation of Q. Okay, if you think about it. And the strange thing is that they never appear together in Fourier transform. So the Fourier transform behaves very differently from you know the thing that needs to represent the. So this was a surprise to me, but you know it just works out, and the example does this.
Did you find this?
I couldn't sleep on a plane home from the States.
You should invite him.
So what? Yeah. So what you want? So this second property sort of means that you look at the induced subfunctions on x1, x2. You can just get the coordinate functions and the constant function. You can never get something with x1 and x2 appears. Yeah. So I'm almost done here. See if there was something more I wanted to say. So something I don't like, you know, which I really think is a problem, is that I assumed, you know, that we could only satisfy P almost all of the time, right? I mean, the most natural assumption is to say that you can satisfy P all the time. And then my characterization also goes out the window. And the counterexample is parity, because parity with perfect completeness, you know, when you can satisfy all the constraints, it's easy to satisfy all the constraints. So let me write this down. Because if you can satisfy all the constraints, you know, parity is just a linear set of equations. So if you know you can satisfy all, you can actually find it efficiently. And so I don't know what happens if you really assume this nicer promise. And upstream Mostel also goes out the window because it uses unique games and, you know, noise on top of it. So there's. And you can rework I sort of allowed negation for free here, but you can sort of rework the entire thing without negation. And you can get similar theorems, and you also get an if and only if, and you have to redefine trivial algorithm to make it work. If you don't have negation, it's not that you shouldn't compare to the trivial algorithm that flips everything to be 0, 1 with probability half, but you have to maximize over P, any biased sort of flipping algorithm, because negation is not there for free anymore.
But you do have this for 3 sat, right?
Pardon?
You have this for 3 sat.
Like
even if it's given that it's satisfiable, then you can.
Yeah. For the 3 sat is useless with perfect satisfiability. Yes, with its definition. I mean, really, parity is the extreme example there. But for instance, Ryan had to work hard to prove that the next thing up for constraint satisfaction of arity 3, which is a not 2 predicate, that turns out also to be useless on satisfiable instances, assuming D to 1, because your proof proves uselessness, right? It analyzes each of the each of the terms in the Fourier expansion and proves that they're all small.
Is there anything that doesn't prove uselessness? Any proof that we have?
Well, so there is this predicate I mentioned, which is approximation resistant, but which disproves the monotonicity of the approximation resistance.
How does the proof of approximation resistance?
Yeah, so what happens there, that is sort of x1 implies that x2 is not equal to x3, and x1 complement implies that x2 is not equal to x4. This is sort of their predicate. So what happens is you can sort of do a similar thing as I did for this quadratic form. You can make a nice measure on this where x3 and x4 are correlated, but they never appear together in the Fourier expansion of this predicate. So it just happens to be that there's this nice measure mu, such that when you look at the Fourier expansion of this, some terms don't appear and you can't control those terms. Okay, I think that's it.
Questions?
Yes.
So the epsilon has to be small enough before these predicates start getting useful, or?
Well, the quantifiers is, being useful is that there exists a delta such that for all, and some epsilon naught such that for all epsilon smaller than epsilon naught, right?
You get and the epsilon naught somehow depends on like the values that Q takes, or is?
Well, this is P useful for Q, right? And then you really, so of course, it depends on Q.
So you took these Q's and you slid them over in your counterexample, so you just did Q plus some constant, 0.5.
Well, if you add,
Sign,
if you add constants, if you add to constants, things really go bad, right? Then even linear things can be bad, because 3-sat is sort of a linear thing with a constant, right? So, what I really need is that, Q is unbiased, so the expectation is 0. So that you just have to beat 0, and then you can sort of work with Q directly. But if you add a constant, the expectation is not 0 anymore, and then things really go a lot worse.
So I have a sort of naive question, but so there are cases where you cannot do anything beyond the very trivial algorithm.
Yeah.
There are some other cases you can do semi-definite programming.
Mm-hmm.
Now, just not necessarily in this framework, but in the most general framework, is there any other tricks which can go beyond semi-definite programming for some approximation problems?
Well, you can do linear programming. Linear programming, it will be enough for some.
Maybe you should state Raghavendra's result.
Yeah, so Raghavendra's tells you, that there is a sufficiently general semi-definite program will, always get the correct ratio.
So you cannot do better than...
Assuming the unique games conjecture.
Yeah, okay, we assume that.
Yeah.
But...
so it sort of says that, yeah.
But this is probably not the most general framework one can hope for, so...
Well, he has completely general constraint satisfaction problems, right? Over actually not even Boolean domains.
So this includes all the approximation algorithms we are...
No, but I mean, the point is that maybe there are approximation problems that are not CSPs.
They're not CSPs. Yeah.
Well, but I'm in the CSP framework. But for the CSP framework, we know what the optimal algorithm look like, but we can't really evaluate it, right? It's
even beyond CSP, there are some further tweaks.
Greedy algorithms.
Well, yeah. Now, if you go beyond CSPs and just talk about the approximation algorithms, there's a. I mean, what's an approximation? There are lots of approximation algorithms, right? Traveling salesman problem. We have,
But within CSP, this is the end of the story. So
well,
even a little bit beyond. I mean, there are results which apply when your underlying variables are not Boolean or constant things, but if you want to find a permutation satisfying a collection of constraints, still these kinds of results extend.
There's a one-box word, which is also tight.
Pardon?
They're shown to maximize a submodular function over a metric constraint. Then they have an algorithm, and it's also tight.
What is 2 approximation?
No, it's 1 minus 1 over E approximation. I mean, E over E minus 1.
Well, yeah, but there are lots of approximations. But is this a trivial? I mean, what's nice with CSP is that we really have trivial approximation ratios that algorithms that are very easy to analyze, right? Just don't look at the instance, flip coins for your variables, and be happy.
But also, I mean, there are CSPs where just deciding if you can satisfy all the constraints is not known to be in P and not known to be NP complete. And probably it's in P, but we don't have the algorithm.
Or this, if you go to bigger domains. Yeah, this is another big industry. If you look at big domains, it's not even known that all problems are, the exact satisfiability problem is NP hard or NP. But that's a different branch, right? So here, all these problems are essentially NP hard. That's the very trivial ones. Pardon?
Looking for T.
Any further questions?
Thanks again.